The busiest part of a city doesn't seem a likely place to study geology. But the urban landscape does offer striking examples of how earth materials are used every day. If we observe closely, we can see how human ingenuity has fused glass into windows, poured concrete into molds, forged metal into sculptures, and fashioned an incredible variety of objects that enhance our everyday lives. And here, an historic building is made from magnificent stone blocks. Its facade reveals a wide variety of earth materials. We probably don't realize just how many of these come from a special group of earth materials we call minerals, building blocks of the earth. To learn more about minerals, let's visit a rocky canyon where erosion has cut deeply into the mountains and exposed this outcrop by the side of the road. This team of earth scientists, a geologist and his 2 students, have found a place that's ideal for studying and collecting. For here, large and spectacular minerals are the key ingredients in this coarse-grained granitic rock. We can define minerals as a set of naturally occurring earth materials that are solid, not a liquid or a gas, inorganic, that is, have never been alive, and are composed of either a single element or compound arranged in a definite and fixed pattern. In other words, any one mineral always has the same recipe. So the composition of the common mineral quartz in Colorado is the same as the quartz found in California. Like all matter, minerals are made of chemicals. If we look closer, we find that the smallest units of minerals are called atoms. Just as the process of combining individual bricks determine the architecture of a building, so too does the arrangement of atoms determine the architecture or structure of each and every mineral. Here's how. Minerals are arranged in 2 basic forms, as just one type of atom called an element, or as combinations of different elements called compounds. In either case, the atoms are bound with each other to form larger combinations of atoms called molecules. The building blocks of minerals, elements, and compounds determine the properties or physical characteristics of any given mineral. For instance, we know that in order for a mineral to grow, specific atoms must be involved in definite combinations. Watch closely. When we dissolve common table salt, or the mineral halite, in a dish of water, the sodium and chlorine atoms break apart. Then, when we allow the water to evaporate, we observe the recombination of sodium and chlorine atoms into tiny cubic-shaped halite crystals. Crystal form is an important mineral property. Other types of crystals grow where molten rock cools below the Earth's surface, an extremely slow process that gives atoms sufficient time to organize into definite crystal patterns. Can you see how this interlocking arrangement of minerals looks a lot like the granite we saw earlier? Another way to learn about the internal arrangement of minerals is to see how they break or cleave. No matter how many times we break halite, we see that its overall structure remains the same. So regardless of their size, all pieces break along planes of weakness, a property referred to as cleavage. With over 2,000 known varieties of minerals, it's useful for mineralogists, the scientists who study minerals, to classify them into families or groups. The major families we'll look at are the silicates, the carbonates, the oxides and sulfides, and finally the native elements. As these names suggest, mineral families are grouped by the kinds of atoms they contain. Let's take a closer look. The Earth, as we know, is covered by a relatively thin crust, or lithosphere, that contains all the Earth's rocks. If we could peel away this rocky crust, dump it in a crusher, and grind it up into its individual elements, we'd come up with the following proportions. Oxygen is by far the most abundant, silicon the second, and aluminum the third. Iron, calcium, sodium, potassium, and other elements make up the rest. In fact, 98.5% of the mass of the Earth's crust is made from only 8 elements. The fundamental building block of all silicate minerals is the silicon-oxygen molecule. This shape allows the most efficient fit between a small silicon atom and its shared 4 larger oxygen atoms. This grouping is often referred to as a silicon-oxygen tetrahedron because the oxygen atoms define the 4 sides of a pyramid. Like the bricks of sidewalks, buildings, and walls, silicon-oxygen tetrahedra are arrangeable in a variety of combinations. The silicon-oxygen tetrahedron combines with other tetrahedra by sharing oxygen atoms, and may often combine with one or more other elements to form the silicate minerals. Let's take a closer look. By seeing how silicon-oxygen tetrahedra are linked together, we can group silicate minerals according to their internal structure. For example, some tetrahedra are linked as chains or ring-like structures to form minerals such as tourmaline. Note the ring-like architecture of these silicon-oxygen molecules. Or tetrahedra may combine into sheets, stacked above each other in multiple layers. You can easily see how the mineral muscovite, or mica, splits into thin, flaky sheets. Muscovite cleaves along flat planes because the atomic bonds within the layers are strong, while the bonds between its layers are extremely weak. The strongest, most stable of the silicate minerals is also the purest, a compound whose silicon-oxygen tetrahedra are linked with each other in a 3-dimensional cage-like arrangement. This is the mineral quartz. The chemical formula for quartz has 1 atom of silica to 2 atoms of oxygen. Note how the pluses and minuses cancel each other out. Because quartz has no extra charges, it has a tightly bound structure with no internal weaknesses. Watch closely. We say that quartz has a conchoidal fracture, a distinct mineral property that results in unpredictably curved breaks. Quartz can, however, grow into magnificent hexagonal crystals. Color is often a useful property for identification. But because quartz occurs in so many colors, such as opal, chert, and amethyst, using color alone to identify it can be misleading. So to properly identify quartz, it's necessary to rely on its unchanging properties of fracture, hardness, and its distinct glassy luster. In fact, the transparent nature of quartz and its relative hardness make it the ideal ingredient for eyeglasses, windows, and mirrors. Most everywhere we look, we find quartz in more places than any other mineral. Why? Simply put, quartz is one of the most durable minerals known. Over time, it resists rusting, physical weathering, and the constant battering by rivers and waves. Is it any wonder this beach sand is nearly pure quartz? Another important rock-forming mineral, feldspar, also belongs to the same group of silicates that have a network-like arrangement of silicon-oxygen tetrahedra. It's a group that accounts for more than half of all Earth's rock-forming minerals. But unlike quartz, feldspar succumbs to physical and chemical weathering because it has a weaker internal structure. Note how feldspar accommodates slightly larger atoms into its crystal structure. These replacement atoms in the feldspar group produce a wide range of similar minerals that are easily distinguished by their characteristic colors. And so, for the feldspar group, color is an important physical property. Now that we've learned about the minerals that contain the most common elements, let's turn to the groups that make up a smaller, yet more economically valuable portion of the Earth's lithosphere. To learn about the other families of minerals, let's follow our team as they visit yet another place on the Earth's crust. Our next stop takes us to a rock quarry, where minerals are removed from the Earth's crust for processing into a variety of useful products. Here we find the sedimentary rock limestone, a rock composed almost entirely of one type of mineral. That mineral is calcite and has physical and chemical properties very different from the silicate minerals we studied earlier. Calcite and the chemically related minerals belong to a family called the carbonates. A closer look shows that the internal structure of calcite is the combination of calcium atoms and carbonate ions, an arrangement whose outward form is a rhomb-shaped crystal. Notice how soft calcite is, a property which distinguishes it from feldspar, quartz, and other look-alike minerals. Another interesting property of calcite is its ability to bend light in two ways so that images appear doubled. Minerals in the carbonate family are used as raw materials in common products such as cement and fertilizer. Another family of economically valuable minerals is the oxides. Their chemical structure is made up of negatively charged atoms of oxygen, bonded to positively charged metallic atoms such as magnesium, aluminum, or iron. If iron is the dominant metal, the mineral magnetite can form. The fact that this mineral attracts paper clips leaves no doubt that magnetite is rich in iron atoms. Like many oxides, this specimen of magnetite has a metallic luster, that is, a shiny metal-like appearance. Its powder leaves a characteristic black streak when the mineral is rubbed on an unglazed porcelain tile. These properties, luster and streak, help us to distinguish many metal oxides from each other. Iron and other ore minerals are highly valued for their properties of strength, flexibility, and electrical conductivity. From construction to electronics, and from tools to automobiles, oxide minerals find their way into countless uses in modern-day society. A class of minerals closely related to the oxides are the sulfides. Sulfide minerals have a combination of metal and sulfur atoms. For example, if molecules containing iron and sulfur are allowed to grow freely, impressive cubic crystals of pyrite like these can form. But don't be fooled by pyrite's yellow color and metallic luster. Even though it looks like gold, it's not, for gold belongs in a class all its own, a group called the native elements. This fourth and final family of non-silicate minerals are named native elements because they're composed of only one type of atom. For example, the precious mineral gold crystallizes where the element Au is concentrated in igneous and metamorphic rocks. It's also found where gold-bearing rocks are eroded and then deposited as nuggets or flakes in a stream. Prospectors who pan for this precious metal are familiar with one of gold's most celebrated properties, its high specific gravity, or density. With skill, they sift the sediment, capturing only the most dense nuggets at the bottom of the pan. This old-timer can't wait to stake his claim. Gold's softness, malleability, and resistance to chemical attack make it a highly prized earth material for use in jewelry, dentistry, satellites, and even as a paper-thin layer on the roof of this state capitol building. Another well-known native element is graphite. Graphite's properties of slipperiness and softness make it an ideal lubricant, and of course, the time-tested writing instrument. But in the high temperature and pressure environments found deep below the Earth's surface, the same carbon atoms arrange themselves into brilliant crystals that are radically different from graphite. The result is the mineral diamond. Diamond is a strongly bonded arrangement of carbon atoms, a net-like structure that make it the hardest earth material known. So hard that diamond-studded drills are used to bore easily through solid rock. Clearly, the arrangement of atoms determines whether a mineral is soft, as graphite, or hard, as diamond. Although we've seen only a few examples of the 2,000 known minerals, we now have a clearer picture of how atoms combine in a variety of ways to produce these amazing substances we call minerals. We've seen that many minerals have physical properties such as color, luster, hardness, streak, and crystal form, while others also have unusual properties such as the ability to fluoresce in the presence of ultraviolet light. And we've seen the many useful and interesting ways in which minerals serve us in our everyday lives. The search for new sources of minerals, however, grows increasingly difficult and complex as we begin to explore new frontiers under the oceans, in remote land areas, and even beyond Earth itself. But remember that minerals, like all Earth materials, are a finite resource. They are non-renewable on a human timescale, so we must use them wisely. Recycling aluminum, glass, copper wire, or even discarded automobiles all help preserve our treasure house of minerals. Just as atoms are the building blocks of all matter, so too are minerals the building blocks of rocks, that thin layer of crust we depend on for all humanity.